Hi everyone, my name is Gabriel Aguiar Tawil, and I'm here to present my CUSRA project for last summer, which was 2020. So I worked in Dr. Kwan's lab, and my project had two main focuses. The main one was computational and lab work. The computational work focused on the identification of a geotachycoccus OLT mutant that had higher affinity for short-chain fatty acids. And the lab work involved the purification of Bacillus plumulus phenolic acid decarboxylase. So I'm going to start with my computational work. So I used three main software tools to achieve my project. I used PyMol for the visualization and the mutagenesis simulations, Autodoc, so that was to calculate the binding affinity, and Caver 3.0, which is used to identify and map out channels, substrate channels, which are used for the various selection of the mutations. So the methodology. So the first idea was to get baseline data. I was comparing caprylic acid to myristic acid, and the idea was to bind those to the wild type OLT. And OLT is an enzyme that decarboxylases a fatty acid. So you end up with the terminal olefin as your product. Then we want to collect the mutation data. So that point was to then identify possible mutants with Caver, then screen them for binding affinity and see the tertiary structure if it had any issues, which was the case for some, so they were ignored. Not ignored, but we couldn't really look too much more into those. And then the identification of possible combinations. So once we screened them for single mutations, we looked at double mutations and triple mutations to see if it would increase the affinity much more. And then just expand a data set and collect the data for multiple lengths of fatty acids. And I did between 5 carbon and 20 carbon to see which point the mutations were the best. And then comparing to the different sets to see which mutations were better. Just a few important notes. So the mechanism, suggested by the mechanism and backed up by what we saw, you can't increase the affinity for shorter fatty acids without increasing that of longer fatty acids. So while the goal is to increase that of the 8 carbon fatty acid to match that of the 14 carbon fatty acid, we cannot get to the point where the 8 becomes better because you can't improve one without improving the other, for at least what we saw. And then also computational results can be inaccurate. Again, these are mathematical simulations. It's not a lab work, which would make the results much easier or much better to work with. And also, affinity doesn't necessarily mean better efficiency. The idea behind using affinity was if you compare the affinity of the substrate to the affinity of the product, you want a higher binding affinity of the substrate than the product, because that suggests that a better efficiency. But the issue with that is that that's not necessarily what we're seeing. This is just for the screening of the different stuff before different ligands before looking at lab work. So myristic acid was shown to have better binding affinity than other fatty acids, with the affinity energy to the wild type being negative 7.3 kilocal per mole, and this was done using Autodoc. And caprylic acid, which was 8 carbons, was found to have a lower efficiency than myristic acid, with an affinity of minus 6.1, again according to Autodoc. And so then I was looking at mutation data. So this is for the single mutations. I looked at 130 different mutations. 62 had decreased affinity, 55 had no change, and 14 had an increased affinity. And these were based off this Caver output. And by saying that, I mean Caver maps out substrate channels, and that includes the binding pocket. So yes, we're just looking at enzymes that really were either attached to the binding pocket or very close to the binding pocket, but found in one of the substrate access channels. And so of all these single mutations, A24249Y was found to have prove the binding the best with an energy of minus 6.8 kilocal per mole. And using this data, we combined it with different ones, all different mutations, to see if those had a greater effect. So of these, 39 combinations were analyzed, either double or triple mutations. 3 showed an increase, 2 had no effect, and the rest had an increased affinity. And these were based off the single mutations that increased efficiency. So for example, let's say we had 2 that each increased the affinity. We want to see if together they increase the affinity even more. So as you can see here. These are the 4 mutations that had the greatest effect, and all of them had all of them maxed out the energy at minus 7.4 kilocal per mole, and only A249Y slash I74F and A249Y and L295W were observed further because of redundancies. As you can see here, they had the same binding efficiency as some of these triple mutations. So the triple mutations that seem redundant because of this were no longer observed. Okay. So I'm just going to go over the comparison between the substrate association constants and the product association constants. So as I said before, this is the small kd, not the capital kd. This is really just the dissociation constants of the ligands to the enzymes. And so if you look at this, again with the focus being 8 carbons, there is a bigger difference between the 8 carbons between the substrate and products than the other ones. And so this is why later on the conclusion will be that A249Y alone is the best because it has the greatest difference between the substrate binding constant and the product binding constant. Even though overall the 2 double mutations do have better ones all down the line, but over here at 8 carbons, it's pretty much the same, and if not slightly better. And so overall, my conclusions for this were the most efficient mutation would be the A249 single mutation. Multiple mutations work too, however, the greatest difference comes from A249 mutations, and the others increase the binding marginally. That can be seen on the last slide. I'm just going to go back. So yeah, so as you see here, there's the greatest increase. The rest kind of taper out at a certain point. Yeah. And then A249F would be good to look at because it's very similar binding energy to A249Y with minus 6.7 kilojoules per mole at 8 carbons. So it's very similar to that of A249Y, but it's slightly less. So that wasn't looked at much more. So my project also had a wet lab component to it. And so as I mentioned before, it involved the isolation and purification of an enzyme being studied, which is SAD, synaptic acid decarboxylase. So in nature, it converts synaptic acid from canola oil to cannonol, but it can also be used for different reactions on phenolic acids, as it belongs to the phenolic acid decarboxylase family of enzymes. So what we're looking at is the conversion of ferulic acid to 2-methoxy-4-phenol, which is a industrial precursor. And as you can see in this mechanism and in this this model, some notable residues are tyrosine 31, 11, 13, and glutamate 64. And these were being looked at, these are the different mutations being looked at that I was isolating. And the idea was to look at the effects of these mutations on the kinetics and seeing how that would affect the efficiency of the enzymatic efficiency of this molecule. And so these results are my purifications. So as you can see, there's 2 protocols. So parent protocol 1 and parent protocol 2. So the idea behind this was that parent protocol 1 was used LB media and nickel NTA beads through affinity chromatography to isolate the different proteins. But we was found that the purification was not the best. The yield was low. But then parent protocol 2 used TB media, which stands for terrific broth, and it's a slightly richer version of LB, and with cobalt beads for the affinity chromatography. And as you can see here, there's a higher yield, but also some more impurities, but that comes with the higher yield. And for example, these also had very typically higher yields than the parent protocol 2, as these use parent protocol 2, but at the same time, this one was similar to the first one. And so that's pretty much it for that lab work. Some improvements that can be done is the use of FPLC, because that just has to have better isolation than gravity columns, and size exclusion chromatography. For example, for these, to purify it afterwards, we use size exclusion chromatography, but that was really after we pooled all the samples. But initially, it was just the affinity chromatography, and so this was all the pooled samples from parent protocol 1. As you see here, the first 2 fractions had a fair amount of impurities, and seeing as they're different in mass from from what we're looking for, which is this band. Using size exclusion chromatography could have gotten rid of these from the beginning. So that's just an improvement we can do in the future. So these are the references I had for the few references I had in my presentation. I would like to thank you for listening to my presentation. I would like to thank Dr. David Kwan for letting me supervising me in his lab this summer. And I would like to thank the CUSRA for selecting me as a candidate for this award. And I really enjoyed my experience, and have a great day.